Hi, and welcome back to the Undivided Attention Workbook. This video is going to go through both chapters 4 and 5 to kind of seal the deal for all the information that you've processed so far from chapters 1 through 3, where we're really diving into what is the neurology of ADHD? How do you understand your brain? And I think it's important for people to understand this because you understand how your heart works. You understand how your muscles work and how digestion works. You learned all of that in school. But you did not, most likely, learn much about just how your brain works. So let's get into it. So how do the regions of the brain work together? The answer is neurotransmitters. So neurotransmitter is a chemical that travels around the brain and functions as the signal between the neurons, which are the fundamental units of the brain, this is kind of an image of a neuron here in this slide. And there are two, maybe actually three, key neurotransmitters relative to ADHD. And they are dopamine and norepinephrine, as well as serotonin, which we'll get into. But you've probably heard about dopamine before, but to better understand really what dopamine does, it can help to learn about norepinephrine. So norepinephrine is made from dopamine. So norepinephrine is synthesized from an enzyme that interacts with dopamine, chops a little piece of dopamine off, and then you've got norepinephrine. And this happens in the upper area of the brainstem. That's where it's produced. And it's released when the body is stressed or if there's a new stimulus coming in. And it's also known as noradrenaline. It travels to almost all areas of the brain, starting in the limbic system. In the limbic system, it triggers the amygdala and the hippocampus to access memories. It also triggers other areas of the body to get ready for fight, flight, or freeze by keeping us on high alert. As it travels forward and up to the frontal lobe and beyond, it turns up the volume on all stimuli coming in. It's an amplifier. It amplifies everything that we are experiencing in our environment. And norepinephrine is how we pay attention. So in order to keep ourselves safe and to survive, our brains need to be able to take everything in from everywhere at all times. In the prefrontal cortex, norepinephrine seems to help us consider the future. If you remember, the limbic system has no ability to consider the future, really. It's only concerned about the past and right now, really. But in the prefrontal cortex, this is where we can consider, the future and future consequences of actions. And norepinephrine does seem to help us do that in the prefrontal cortex, but only if dopamine is there too. And dopamine does that by quieting the noise that norepinephrine is amplifying. And that helps us prioritize what of everything that is happening in our environment and in our body is important. So, the other important thing here is norepinephrine neurons, as they exit the brainstem, first travel through the section of the brain where serotonin neurons come out. So norepinephrine actually governs over the serotonin system. So here's the recap. Norepinephrine. Norepinephrine is how we pay attention, non-specifically. It helps us with alertness and it regulates our energy. It's involved in working memory, which is the mind's eye, the mind's voice, the mind's heart, and the mind's playground. And it is responsible for fight or flight. Norepinephrine is kind of the first trigger for fight or flight that then in the limbic system, and then that triggers the rest of the body and adrenaline, et cetera, et cetera. It is triggered by stress or an encounter with a new stimulus, and it has a role in regulating serotonin and thereby mood. So let's move on to dopamine. Dopamine is made from the protein L-tyrosine, which we ingest. And actually, it's made from phenylalanine and then L-tyrosine. But anyway, it's made from a protein that we consume. And that happens in the upper part of the brainstem again. Dopamine does not spend much time in the limbic system at all. There's virtually no receptors for dopamine in the limbic system. And there are also almost no receptors for dopamine in the areas of the brain that take in our senses. So past the frontal cortex and the motor cortex, there are almost no dopamine receptors in the parietal, temporal regions. It is, however, highly concentrated in the prefrontal cortex and the primary motor cortex, which is just above the prefrontal cortex. So, as you recall and can guess by its name, the primary motor cortex is the area that makes us move, right? In the prefrontal cortex, dopamine seems to make decisions about whether something is as good or better or worse than our expectations. And this is called reward prediction. Dopamine is the go signal from the prefrontal cortex and motor cortex to the body. It tells the body to do something that may involve reward. Dopamine is not the actual reward. The other chemicals like endorphins and so on are released from the reward, but dopamine helps us do the things that will get us there and give us those chemicals. So to recap, dopamine is responsible for motor behavior. And so this is task initiation, controlling behavior in response to emotion. It is how we take action. It is how we move. It's movement. It's involved in reward. And long-term rewards require foresight or mind's playground. It's also involved in motivation. It's how we can be motivated to achieve a reward. And it helps norepinephrine amplify less of everything coming in from everywhere. It helps us prioritize what is important. So, in order to adhere to the universal timeline, we need a typically developing prefrontal cortex to always hold the future in mind with appropriate levels of dopamine and norepinephrine to counteract the instincts of the limbic system, which has no ability to consider the future and is governed by emotions, fear, and desires, and like what's happening right now in the environment. So, putting it all together with ADHD, and I think this is a perfect meme for just ADHD in general. My brain is like an internet browser. I have 17 tabs open, 3 of them are frozen, and I have no idea where the music is coming from. Taking out the brain and telling it to shut up. Yeah. So, how is the ADHD brain different? We have a smaller prefrontal cortex. It's just smaller. By not very much, maybe 15%, but it's enough to have a significant impact. Our prefrontal cortex develops/matures 30% more slowly than our same age peers. So therefore, an 18-year-old can act like a 12-year-old, a 50-year-old more like a 35-year-old. We're late bloomers. We are developmentally delayed. Dopamine and norepinephrine are dysregulated and out of balance due to structural differences in our brain. We have a significant dopamine deficiency in the prefrontal cortex. Our brains seem to have less overall electrical activity. We have brain waves that dip down into the patterns that are present during sleep throughout the day. Throughout the day, we're trying to be awake and alert, and the brainwave patterns just go dip. We're just like constantly falling asleep. So our brain is struggling to stay awake and maintain alertness. Our brains have higher metabolic needs, and we burn through glucose, which is, what the brain needs for metabolism, glucose. we burn through glucose more quickly, and we need more frequent nutrient inputs to sustain energy, attention, and so on. Our cognitive resources deplete quickly, and we have to maintain that with frequent nutrient inputs. There are also other networks in the brain that are activated at different times, and this is called the dual process theory. In the dual process theory, you have system 1, which is called the default mode network. And this is the system that's firing when we're not engaged in any kind of, task. We are just thinking and feeling. We're observing our environment. It's where we're thinking about ourselves, and thoughts and cognition kind of come together. Then there's system 2, which is the task functional network. And that activates when we have to deliberate and use rules and constructs that we've learned before to complete a task. It's more intensive. It's more, cognitively, it uses more cognitive resources. In a neurotypical person, System 1, or the default mode network, where emotions and cognitions kind of come together and it's observing the environment and it's based on now, that should quiet down and shut up during the task. But in ADHD, it never turns off. The default mode network is always active. Therefore, we always have irrelevant thoughts, irrelevant feelings, irrelevant sensations interjecting into everything that we are trying to do. And that is why, when we tell a story, we start here, but it goes bing, bong, bing, 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 bong, bing, bong, bing, bing, bong, because we operate on association constantly. I think the only time the default mode network quiets down for us is when we really get a hyper focus. But yeah, the default mode network is always interjecting irrelevant feelings into tasks. It doesn't matter how you feel about the dishes. They just need to be done, right? But we are more wired for fight or flight. We are more arousable. We're more hypervigilant. We're more sensitive to threats, especially emotional ones. We have less ability to choose what's important in terms of the stimuli that's coming in, and we're less able to do things that benefit our own future. And this is exhausting. We are more reptile brain. With dopamine and norepinephrine dysregulated in the prefrontal cortex, people with ADHD can, at baseline, experience a sense of languishing. And languishing is the opposite of a sense of wellness, but it's not quite illness or frank depression. And some people describe this feeling as being overstimulated and understimulated at the same time, or chronic low-grade frustration. It's a bit more than feeling bored. It's just kind of meh. And our reward and pleasure system, which is also called hedonic tone. Hedonism is like experiencing pleasure. Our hedonic tone seems to have low sensitivity. And without a good mind's playground, we cannot predict rewards that are too far away in the future. And due to poor working memory, we may have recognized rewards in the past, but then we forget they exist. But our hedonic tone, if this is 0, a person with a neurotypical brain has a hedonic tone that idles just above 0, right? I mean, it doesn't take much for a person with a neurotypical brain to just have a baseline state of everything's fine. I'm experiencing pleasure in just about everything. ADHD brains, hedonic tones idles below 0. We're down here, so in order to get us up to where we're sensing pleasure and reward, it takes a lot more. And finally, the area of our brain that takes in our senses, the parietal lobe, is responsible for how we understand where we are in space and time. So the parietal lobe, dysregulations of neurotransmitters here impairs how we experience time. I think I was supposed to read that here. But anyway, So, chronic sense of languishing, low hedonic tone, poor sense of time, we're more reptile brain, we're more wired for fight or flight, and we're less able to think about our future and consider consequences of what we're doing right now and how that's going to affect us 5 minutes from now, an hour from now, 5-10 years from now. It's very difficult for people with ADHD to envision themselves in the future. It blew my mind when I learned that neurotypical people can literally hold the future in mind basically at all times. I don't think I can really ever hold the future in mind. Not for more than a few moments. And, if I'm not looking even at my calendar just for the day, if I am not looking at it at that moment, when I turn away, I really have a difficult time knowing what is on my agenda for the rest of the day. And this is something that people with ADHD experience commonly. So that's ADHD brains. That's the summary of ADHD brains. And in the next chapters, we're going to talk about what can you do to manage all of this stuff that is happening in your ADHD brain. So stay tuned for that.